I'm Mike, and with me is my colleague John. First, we would like to thank NASA for hosting this event. We're very proud to be with our peers from across the nation here at the Kennedy Space Center. In our presentation, first we're going to go through our design and decision processes. Then we are going to elaborate on our final design. To do this, we have broken the robot down into subsystems, which come together to create the system, a planetary excavator. As we discuss these subsystems, we will point out some unique features which we hope will stand out. Design process. One challenge that a new team faces is establishing a team culture and structure. We know what we want it to be. We want it to be organized, document, research-driven, and create a rewarding experience for our student members. To do this, we use two primary pieces of reference material, the NASA System Engineering Handbook and the NASA Spaceflight Program Project Management Handbook. Some tools that we gathered from this were some technical management concepts, work breakdown structures, and scheduling concepts. One quote that I really liked from the NASA Spaceflight Management Handbook was that peer reviews that are really small and really informal are the most productive. And this is what we really want to go for. We want to set the parameters that we're going to be research-driven, and that's how we're going to make our decisions. But we want people to be comfortable and feel free to contribute throughout. We also want to have a strong systems engineering approach. A system that, as a student, we work in many teams as an engineering student. Some teams get caught up on theory. Some teams rush to build something before they know what, fully understand the system. I think the system engineering process offers a way to bridge these two. I think the program life cycle is a good way to do this. So when we started last summer, we started with pre-phase A, which is concept studies. We like to think of pre-phase A as the what. The what do we need to know to create a planetary excavator? Then we took these whats and built them into phase A, concept studies and development, where what we like to think of it as like finding our findings, something like analogous to doing a problem on a piece of paper, something that we would see in school. From now, our phase B design can be guided by pre-phase A, and our fabrication can be guided by the design. Our testing can be guided by these previous findings as well. Each phase builds on itself, the previous one. And here we are in phase E operations at the Kennedy Space Center. Here we have a work breakdown structure. I picked this one out as something that was especially important because it's an example of a system engineering concept. It will also help guide the presentation, the following slides of the presentation. Our planetary excavator is broken down into three subsystems. We have a lower assembly, an upper assembly, and hardware. The lower assembly consists of the chassis framework, the drive configuration, and the wheels. The upper assembly consists of the dump system, the upper assembly framework, and the excavation mechanism. Our hardware consists of communications, controls, and power management. So the first thing that I think we really wanted to hash out was, well, what we noticed from this competition was there was two primary mechanical engineering challenges, locomotion and the excavation depositing cycle. So to design specifically a planetary excavator for these conditions, we needed to thoroughly understand what went into these parts. So I guess the first, most obvious one would be tracks or wheels, right? So we looked at compact front-end loaders as a case study. We looked at journals that took input from industry experts, and they talked about the difference because tracks are a growing mode of locomotion in these. They said that tracks provide a greater traction, but they have increased maintenance, which is definitely not something we want on a planetary excavator where we can't, per se, maintenance it. Also, it was said that additional traction becomes less impactful while working on dry, sandy terrain, which is something that I think is, on Earth, more or less something that we can kind of make an analogy to this condition. So now that we had our wheels, we had to decide what constitutes the optimal wheel. First, we found that a spherical wheel provides additional traction when compared to a cylindrical rigid wheel. This is because of the increased surface area, basically. We also found that many shallow lugs, lugs or grousers, the traction that goes on the wheel, creates a more efficient traction profile than long lugs because of the slippage which the longer lugs will create under the soil, under the robot. With this, we also looked at past competitors. With this, we saw that some teams had buildup behind their lugs with reglets sticking to it. So to account for that, we created a channel so that the reglet would not build up behind our wheels, impacting our traction. So now that we have our wheels, we need to understand what does driving on deformable terrain mean. To do this, we looked at the Becker model. The Becker model for driving on deformable terrain breaks down this into two components: compaction resistance and bulldozing resistance. Compaction resistance simply is the soil being forced under the wheel as it rotates. Bulldozing resistance is the contribution of the soil being pushed forward by the wheel as it moves. So if you take the soil geological parameters, your robot parameters, you can start to build a profile of what you could be expecting for driving on this deformable terrain. So here we have some of our findings, and then we can compare it to our drive configuration with our DC motor and see where we're going to lie with a certain expected torque, or with a certain expected torque. Since we use brush, we like to use the analogy that they're hungry. They'll climb up to the required torque so we can see what our RPM is going to be and what our current is going to be. And we can look at our max conditions so we can stay well below that. The next big challenge that we talked about was excavating. So how can we quantify our excavating? We use two models, the Bolonev model and the Swick renewable model. These are empirical models, so each of them eliminate one parameter. For instance, the Bolonev model is a 3D model, but it doesn't account for speed. The Swick model is only a 2D model, so it doesn't have the bucket geometry, but it does take speed into account. And we can see the two different results that these two models yield. So one thing that's very interesting about the Bolonev model is you can actually set it to model a bucket that's submerged. So I think that a good way to look at this would be the Swick model. We like to think of it as maybe this is what would happen as we're breaking ground. And the Bolonev model would be something more analogous to once we're all the way submerged. So now with this, we could take our expected values and design an excavation mechanism using a drive and gearing configuration so that we can design specifically for excavating regular. Our upper assembly. So as we were talking before, first we need to isolate what is our excavation mechanism. How are we going to do it? We isolated a bucket wheel and a bucket ladder as two methods which we thought were optimal. I think they're optimal because they allow you to excavate and you're not restricted by the weight of your excavator. A quote that explains this powerful idea from Advantageous Bucket Wheel Configurations for Lightweight Planetary Excavators by Carnegie Mellon says, "Continuous excavators do not suffer from increased resistance from soil accumulation because a new bucket is repeatedly introduced into the cut soil. So in this way, you're not restricted by the weight of the robot as to how much you can dig. So in this fashion, I think that either a bucket wheel or a bucket ladder was optimal. Now that we had our method of excavating, we identified a second area which we thought could be a potential area of failure, which is the upper assembly framework, which you see here. Now the upper assembly framework is subjected to some decent loads because we have an excavation mechanism here and a container basin here, which would have a load and a moment arm around the axis of rotation. So to do this, we treated this upper assembly framework as a steel structure. We used FEA. We actually used SAP 2000 because this was a pretty complex assembly. So to account for the dynamic nature of this actuator going up and down, we created a static equivalent system, created our model, and then conferred with this Department of Civil Engineering at University of Illinois, Chicago. After our model was validated, we adjusted the wall thicknesses and the material use so that we could have what we see here, which is primarily blues, greens, and yellows, which is safe. The lower assembly serves three main purposes. We wanted to build it around our drive configuration, one of the primary mechanical engineering challenges that we mentioned earlier. It also has to house some electrical components and enclose these components from the outside. We also used chromoly alloy steel so that we could have a thinner wall thickness, but still maintain the strength properties. In this way, we hope to reduce weight. Additionally, with these models, we can also create a power profile so that we can take our hypothetical current draws from digging and driving and see how much power we need. And that is how we spec our battery. With this, I'm going to pass it to my colleague John, who's going to elaborate on some of the more electrical and computer elements of this project.
Thanks, Bailey. Or Michael. Coming to the communications component of the design, the communications goal was to design a method that would minimize minimize bandwidth consumption and reduce packet loss. To do this, we had to do one-way communications. And doing one-way communications from mission control to the robot, I know prevented a crosstalk issue, and it became useless in the capacity that any statuses that were on the robot could be easily observed on the monitors in mission control. As well, we also decided that utilization of a user datagram protocol over a transmission control protocol, EDT or TCP, would have been was the better choice. In this case, UDP does not it neglects packet loss in the case of lost data, where TCP will attempt to reestablish connection by transmitting the same data over again. By doing this, we can cause a backlog effect that can actually cause the robot to catch old commands that could then confuse the system and not do what the operator wants it to do. As well, the bandwidth would then be halved by handshake requirements because of UDP's no fair acts. As well, the system would also have an 8-bit protocol, which would minimize the amount of data transmitted in each segment. Each protocol, each command would then only operate one mode at a time, and would also reduce the amount of data lost in the case of interference or attenuation in the signal. Moving along to our controls portion, the control portion is broken up into an electrical and computer aspect. Starting at mission control, we go over the computer aspect. At mission control, we use a teleop system that is built off of a software application development library that and toolset for C++ and Python, known as Robot Operating System, or ROS for short. For our case, we use Hyper version of this system. This system allows for easy reintegration in the case of in-field operations, such as we need to rewrite an entire command structure. So we're able to respread it and reconfigure the entire system within a matter of seconds. As well, the teleop node is able to, teleop system is able to take Xbox 360 controller data and encode that data and transmit it to the robot. This is done through 3 nodes: joystick teleop, base controller, and the encoder node. The Xbox controller data is then sent first through a driver to the joystick teleop node, which then grabs that data and takes it to an arbitrary, treats it arbitrarily, and hands it over to base controller. Base controller takes that data and places it into a template for the Xbox 360 controller, which is called Xbox message. We hand that over to encoder at this point. Encoder then takes that data and then encodes it into an 8-bit protocol, which is then transmitted over UDP to the robot. Moving along to the electrical portion of the system, the electrical aspects are, there are 2 systems. The signal multiplexer, as you can see here in this housing, and the Robotech motor controllers, which are internalized in the robot. The signal multiplexer, or SIGMUX for short, is a device that takes a signal from the command protocol and is able to then operate as a multiplexer in some capacity, operating either in safe mode, RC mode, or autonomous. For our functionality, we don't use autonomous, but it will be used in a future day. The signal multiplexer is comprised of 2 components: the CC3000 Wi-Fi module and the ATmega32U4 microcontroller. The ATmega32U microcontroller was decided because of its USB functionality, which would allow us to remove hardware components such as an FTDI interface through serial, and would allow us to have serial communication at the same time. The ATmega32U4 has a maximum consumption rate of 10 milliamps at a 5-volt source. This in turn also means that low power consumption makes it a critical component to enhance battery life and performance. As well, the signal multiplexer uses a CC3000 module on board. The CC3000 module is built by Adafruit, but actually uses the CC3000 component of it is actually manufactured by TI. The system on there is a module that can be easily removed in the case of failure and replaced, coming with either an built-on antenna or external. In this case, we are using external antennas. You can see here, it's hooked up to this blue device. That's the 63000. It's able to take UDP, TCP, and any other communication protocol, and consumes at max for our purposes 100 milliamps. Since we are only doing one-way communication, in case we do two-way communication, it consumes at max 300 milliamps, making the total system 130 milliamps when calculated, or up to 330 in full operation. Moving on to the Robotech motor controllers. The Robotech motor controllers were viewed as the most viable option out of several other choices because of several factors. The factors are that the power management systems were linearized, so that it was easier for a driver to actually be able to send the power command to the system and see expected results. With most other motor controllers, they are all an exponential rate, so where movement doesn't occur until a 10% mark or so. In this case, we see a movement at about 3% mark. The Robotech motor controllers as well allow us to have onboard functionality for them. They have many built-in microcontroller functionalities themselves, such as rear limit switches in the back. This facilitates a dumping, so in the case that we get to a wall, we're able to actually act as a reverse limit switch and stop the field from moving in the back, so that the unit can align itself then to the wall, so making the driver's operation be much more simplistic. Another component of the Robotech motor controller is that it allows for RS-232 communications. This is the primary means by which the signal multiplexer communicates to the system. So rather than using a pulse width modulation or an analog configuration, it just uses RS-232 to get a more exact command for exactly what operations it wishes to have. The Robotech motor controller allows for scripting capabilities. So for future operations, if we wish to have telemetry systems on board and PID control, and allow PID controls to be programmed on the fly, we're able to allow that functionality. And that's about it for the electrical report. I'm going to hand it back.
Thanks, John. So one thing that we really wanted to do is have in-house fabrication. This is important because we didn't want to be over-the-wall engineers. We wanted to build tangible, practical, feasible designs. So this was guided by our head of production. And in this way, we could become better engineers because we could physically see what works. We couldn't just build something and send it out. Now we know what works on a more holistic level. This is an example of our design process where we take the drawings to the fabrication to a finished product. Assembly, integration, and testing. Here we brought the subsystems together, which we talked about, and put them all together. Here's one of our members putting it together. We used a sand arena for testing. Although we know it's not a completely analogous material, we thought it would be a good concept verification. Additionally, we did not want to subject our members to potential safety hazards, which is small particles and skin irritant. And it was also a more economically feasible option. Quickly, we're going to talk about some future improvements. Definitely composite materials and other materials are something that we want to look at. Changing some of our gearing and sprockets to a different type of metal. I know powder metallurgy allows some alloys to be created in very efficient ways, especially with the geometry of a gear or sprocket. Also, we're right now working on a chain drive. We've seen some of the challenges that this can present, and also the weight that it adds. So we definitely want to move away from that and reduce our weight there. Additionally, since we're engineering design team, we have multiple teams within us. So we want to take, John actually works with our IGBC team, which additionally does autonomous vehicles. So we've been working with them closely, so we aim to take some of their developments and port it over to our system for the next year. In conclusion, I would like to thank you for your time. To reiterate, our goal as a team was to have a focused systems engineering approach. Our goal was to construct a robot specifically for traversing and excavating regolith. Our goal was to have a process where each step could be clearly supported, guided by analysis and credible source material. Although not an innovation per se, I hope that our research-focused approach, our discrete control system, and our efficient communications has helped us contribute to the competition towards planetary excavation and towards STEM. We are EDT. We look forward to competing this year and building on this experience. We'll now open the floor to questions. Yes?
Yes, thanks for the explanation on like your analysis on the mobility and the excavation, had you used those type of analyses before? And my follow-up to that is, when you did your prototype testing, did you find that your analysis was close?
Well, here's the thing. For sand, it's not an analogous material. Like the sinkage. Sinkage is a big component which builds on how much you push and how much you also slide under. So we can't really say if it's like that. But I think if we take the theoretical approach and look at results now, we can say and we can tune our models more effectively. Additionally, soil is it's random. It's somewhere between fluids and solid dynamics. So a lot of these models, like our excavation models and the Becker model, are actually empirical. So I think they give you a good idea on where you need to be, but I don't know how truly pinpoint they are.
Okay, thanks.
What was your budget for this project?
We operated about $7,000. Initially, we had planned for more because we wanted to build some of the autonomous functionality in there, but there's several challenges, and we definitely want to get a solid product out for the first year.
So did you have any trouble spending $7,000?
Oh, absolutely not.
Did you guys compete last year?
I was with Oakton Community College, and
Did your school participate last year?
no. We
So this is your first year?
implemented this as soon as the competition ended. We got with these guys.
Is this the first year that the school has participated?
Actually, I don't know, I remember hearing IEEE actually said they participated one year and then they gave up on it.
I don't think so.
Okay,
That's
so,
what I
so basically this is your design, you're not building
No.
on a
No,
previous
yeah,
year's?
this is-
Okay.
This was built from scratch.
That's what I was curious of. And then, just real quick, the one-way communication, so, and then you referenced two-way communication, so are there times you're gonna use two-way?
No, I was actually describing what the benefits of a one-way communication over a two-way was.
Okay, so what are you utilizing?
So we're utilizing a UDP transmission, one-way communication. The robot never talks back to mission
So it
control
doesn't.
ever once. So it's only just taking commands. It's just a dummy device.
Okay.
Since the lights are all visible on the system, there's actually a configuration on there that can be easily seen from mission control. So in case that something's going wrong, you can see the lights.
For your excavation system, you said you want to get away from the chain.
Yeah, we had an interesting experience the other day where one of the things we actually made some slight changes. We looked at another off-road vehicle, like mountain bikers, and one of the things they do is they have these chain guards to keep the mud out of their gear. So we thought maybe that would be a good way to reduce to protect our chains. It actually served in the opposite way, and it seized our chains, and we stalled out, and we blew a motor. So it created a bunch of headaches, and something you don't really want. So we can really see now how devastating the right load can be, and having this chain configuration, I think, just compounds that. Even though we did take some steps like self-lubricating, self-impregnated chain, it's supposed to be ideal for these types of scenarios, but nothing compares to right load, I'd say.
What other system would you think about going to instead?
Probably a pulley system. We've been talking to some of the other schools. Actually, we reached out to Iowa State during the project because we reached out to all of them, but Iowa State reciprocated, and we had a Google chat hangout, and they kind of shared some of their experiences. And we would like to, we really like their design and how they overcame this chain problem with their self-fabricated conveyor system, which is something we'd like to do, and we would definitely look to change it that way.
Any other questions?
Where did you manufacture this?
It's actually a retrofitted school bus garage, and we got a mill, we got some bandsaws, we go over to the physics shop. We got pretty good friends with them by now, and we welded all of it together. So it's not fabricated. It's obviously the actuator, the motor, the chains, and the sprockets, but everything else is fabricated. We try to fabricate to a tolerance of plus or minus 5 thou, and especially with components
Plus
that
or
have
minus what?
5 thou of an inch. Yeah. So we definitely take pride in the fabrication of our parts. Yeah.
And well, time's up.
All right, thank you guys.
Thank you.
Thank you.
Thanks.